Several possible causes can explain voltage readings on ground wires. Firstly, ghost voltage, stray currents or residual energy from other circuits or devices can induce a small voltage on the ground wires. This voltage is usually harmless but can cause mild shocks. Secondly, a high resistance ground fault, a weak or intermittent connection between the ground system and the actual earth ground can create a higher resistance path for current to flow. This can lead to elevated voltage on the ground wires. Thirdly, capacitive coupling. Electrical devices and wiring can create capacitance between different circuits. If there is a difference in potential between these circuits, a current can flow through the capacitance and onto the ground wires. Fourthly, neutral ground bonding issues. If the neutral and ground wires are not properly bonded, it can create a situation where current flows from the neutral to the ground wires, resulting in voltage on the ground. Fifthly, improper wiring or grounding. Incorrect wiring or faulty grounding connections can create paths for current to flow through the ground wires and cause elevated voltage. The elevated voltage on the ground wires can pose a shock hazard to anyone who comes into contact with them. It can also damage electrical equipment connected to the ground system. To troubleshoot, firstly, measure the voltage. Use a reliable voltmeter to measure the voltage between the ground wires and neutral as well as between the ground wires and phases. Secondly, check for ground faults. Use a ground fault tester or clamp-on ammeter to verify that there are no high resistance ground faults. Thirdly, inspect wiring and connections. Thoroughly inspect the wiring and connections to ensure they are correct and secure. Fourthly, test neutral ground bonding. Ensure that the neutral and ground wires are properly bonded in accordance with code requirements. If you are unable to identify and resolve the issue, consult a qualified electrician for further troubleshooting and repairs. Understanding these potential causes and employing a systematic troubleshooting approach is crucial for ensuring electrical safety and preventing potential hazards. Ghost voltages, though usually harmless, can be a nuisance during electrical work. They arise from capacitive or inductive coupling between energized conductors and nearby unenergized conductors, like ground wires. The key characteristic of a ghost voltage is that it disappears or significantly drops when a load is applied, because it lacks significant current carrying capacity. A true voltage source will maintain its voltage even under load. To identify ghost voltages, use a low impedance voltmeter. These meters are designed to minimize the effect of high impedance sources, such as capacitive coupling, thereby reducing or eliminating ghost voltage readings. A standard high impedance voltmeter can display these false voltages, leading to misdiagnosis. When troubleshooting, always confirm the presence of a sustained voltage with a low impedance meter before taking further action. Higher resistance ground faults are more serious and indicate a compromised ground path. The purpose of a grounding system is to provide a low impedance path for fault current to return to the source, facilitating the rapid operation of overcurrent protective devices like circuit breakers or fuses. A high resistance connection anywhere in the ground path impedes this flow, potentially leaving hazardous voltage on equipment enclosures and other grounded surfaces. Common causes of high resistance ground faults include corroded connections, loose terminals, or damaged grounding conductors. These faults can be difficult to detect with a standard ohmmeter because the resistance may be low enough to show continuity but still too high to effectively carry fault current. To properly identify high resistance ground faults, use a ground fault loop impedance tester. This device injects a small test current into the ground system and measures the voltage drop. The tester then calculates the ground fault loop impedance. If the impedance exceeds the maximum allowable value specified in the electrical code, it indicates a high resistance ground fault that needs to be addressed. Thermographic imaging can also be helpful in locating high resistance connections, as these points often generate heat due to the current flow. Capacitive coupling occurs when two conductors are in close proximity and separated by an insulating material, forming a capacitor. In electrical systems, capacitive coupling can occur between energized conductors and ground wires, especially in long parallel runs of cable. The amount of current that flows due to capacitive coupling is dependent on the voltage difference between the conductors, the frequency of the voltage, and the capacitance between the conductors. While the current is usually small, it can still create a noticeable voltage on the ground wire. To minimize capacitive coupling, maintain adequate spacing between energized conductors and ground wires. Shielded cables can also be used to reduce the capacitive effect by providing a grounded barrier between the conductors. Neutral ground bonding issues are critical to address as they can lead to dangerous voltage on grounded equipment. In a properly wired electrical system, the neutral and ground conductors are bonded together at only one point, typically at the service entrance. This single-point bond ensures that the neutral and ground are at the same potential. If the neutral and ground are bonded at multiple points, it creates parallel paths for neutral current to flow. This can result in current flowing through the ground conductors, causing voltage drops and potentially energizing grounded equipment. To verify proper neutral-ground bonding, perform an impedance test between the neutral and ground conductors at various points in the system. The impedance should be very low near the service entrance and increase with distance. Any unexpected low impedance readings indicate multiple neutral-ground bonds. Identifying and correcting these unintended bonds is essential for electrical safety. Improper wiring and grounding are fundamental issues that can compromise the entire electrical system. Incorrect wiring can create unintentional paths for current to flow, leading to voltage on ground wires and increasing the risk of electric shock. Common wiring errors include reverse polarity, where the hot and neutral wires are interchanged, and open grounds, where the ground wire is not properly connected. Faulty grounding connections can also create high resistance paths, impeding the flow of fault current and increasing the potential for hazardous voltage on equipment. To ensure proper wiring and grounding, perform a thorough inspection of all connections, verifying that they are tight, corrosion-free, and correctly wired. Use a circuit analyzer to test for common wiring errors such as reverse polarity, open grounds, and hot-neutral shorts. Grounding electrode systems are a critical component of electrical safety, providing a low impedance path to earth for fault current. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete-encased electrodes connected to the grounding system. The effectiveness of the grounding electrode system depends on the resistance to earth. Electrical codes specify maximum allowable resistance values for grounding electrodes. To measure the resistance to earth, use a ground resistance tester. This device injects a test current into the earth and measures the voltage drop to calculate the resistance. If the resistance exceeds the maximum allowable value, additional grounding electrodes may be required. Regular inspection and testing of the grounding electrode system is essential to ensure its effectiveness. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD work by diverting surge current to ground, preventing it from reaching sensitive equipment. SPD are typically installed at the service entrance and at branch panels throughout the electrical system. The effectiveness of an SPD depends on its ability to quickly and effectively divert surge current to ground. To ensure proper SPD operation, verify that the SPD is properly grounded and that it has not been damaged by previous surges. Regular inspection and testing of SPD is recommended. Electrical panels are distribution points for electrical power, and they must be properly grounded and maintained to ensure safety. The panel enclosure should be securely grounded to provide a lower impedance path for fault current. The neutral and ground buses within the panel should be properly bonded at the service entrance. All circuit breakers and other components should be properly labeled and in good working condition. Regular inspection and maintenance of electrical panels is essential to identify and address potential hazards. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. The proper selection and coordination of overcurrent protective devices is crucial for electrical safety. Circuit breakers should be sized appropriately for the circuit they protect and should be tested periodically to ensure they are functioning correctly. Fuses should be of the correct type and rating for the circuit they protect and should be replaced immediately if they blow. Arc fault circuit interrupters, or FSIs, are a type of circuit breaker that is designed to protect against arc faults. Arc faults are dangerous electrical faults that can cause fires. FSIs work by detecting the unique characteristics of arc faults and interrupting the circuit, preventing a fire from starting. FSIs are required in many areas of the home, such as bedrooms, living rooms, and dining rooms. Regular testing of FSIs is recommended to ensure they are functioning correctly. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults. GFCIs work by detecting small imbalances in current between a hot and neutral conductors. If an imbalance is detected, the GFCI interrupts the circuit, preventing electric shock. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Regular testing of GFCIs is recommended to ensure they are functioning correctly. Electrical codes and standards provide detailed requirements for electrical installations, including wiring methods, grounding, and overcurrent protection. Compliance with electrical codes and standards is essential for electrical safety. Electrical codes are typically enforced by local authorities, and inspections are often required to ensure compliance. Staying up to date on the latest electrical codes and standards is crucial for electricians and other electrical professionals. Electrical safety training is essential for anyone who works with or around electricity. Training should cover topics such as electrical hazards, safe work practices, and the proper use of personal protective equipment. Regular refresher training is recommended to reinforce safe work habits. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. Lockout/tagout procedures should be followed whenever working on electrical equipment to ensure safety. Personal protective equipment, or PPE, is used to protect workers from electrical hazards. PPE includes items such as rubber gloves, safety glasses, and insulated tools. The proper selection and use of PPE is essential for electrical safety. PPE should be inspected regularly to ensure it is in good working condition. Safe work practices are essential for preventing electrical accidents. These practices include always de-energizing equipment before working on it, using insulated tools, and maintaining a safe distance from energized conductors. Following safe work practices can significantly reduce the risk of electrical shock and other injuries. Electrical safety audits are conducted to identify potential electrical hazards and ensure compliance with safety regulations. Audits typically involve a thorough inspection of the electrical system, including wiring, grounding, and overcurrent protection. The results of the audit are used to develop a plan for correcting any deficiencies and improving electrical safety. Regular electrical safety audits are recommended to maintain a safe working environment. Electrical maintenance programs are designed to ensure the reliability and safety of electrical equipment. These programs typically involve regular inspections, testing, and maintenance of electrical equipment. The goal of an electrical maintenance program is to prevent equipment failures and ensure that the electrical system is operating safely and efficiently. Electrical testing equipment is used to verify the proper operation of electrical equipment and identify potential problems. Common types of electrical testing equipment include voltmeters, ammeters, ohmmeters, and insulation resistance testers. The proper use of electrical testing equipment is essential for troubleshooting electrical problems and ensuring electrical safety. Static electricity can build up on surfaces and discharge, potentially damaging sensitive electronic equipment. Electrostatic discharge, or ES, can be prevented by using anti-static mats, wrist straps, and other ESD control measures. ESD control is particularly important in environments where electronic components are manufactured or repaired. Harmonics are distortions in the electrical waveform that can cause problems with electrical equipment. Harmonics can be caused by nonlinear loads, such as electronic ballasts and variable frequency drives. Harmonic filters can be used to reduce the level of harmonics in the electrical system. Power quality is a measure of the quality of electrical power. Poor power quality can cause equipment malfunctions, reduced equipment life, and increased energy costs. Power quality problems can be caused by harmonics, voltage sags, voltage swells, and other disturbances. Power quality monitoring equipment can be used to identify and diagnose power quality problems. Energy efficiency is the practice of using less energy to perform the same task. Energy-efficient electrical equipment can save money and reduce environmental impact. Energy-efficient lighting, motors, and other electrical equipment are available. Regular energy audits can help identify opportunities to improve energy efficiency. Renewable energy sources, such as solar and wind power, can be used to generate electricity. Renewable energy sources are environmentally friendly and can reduce reliance on fossil fuels. Solar panels and wind turbines can be installed to generate electricity for homes and businesses. The grounding system ensures a low impedance path for fault current to return to the source. The neutral conductor carries the unbalanced current from the load back to the source. The equipment grounding conductor connects the non-current carrying metal parts of equipment to the grounding system. Grounding electrodes provide a connection to the earth. Bonding connects metal parts together to create an electrically conductive path. Ground fault circuit interrupters protect people from electric shock. Arc fault circuit interrupters protect against fires caused by arc faults. Surge protective devices protect equipment from voltage surges. The electrical codes and standards provide requirements for safe electrical installations. Electrical safety training is essential for anyone working with electricity. Lockout/tag-up procedures prevent accidental energization of equipment. Personal protective equipment protects workers from electrical hazards. Safe work practices reduce the risk of electrical accidents. Electrical safety audits identify potential hazards. Electrical maintenance programs ensure equipment reliability and safety. Electrical testing equipment verifies proper equipment operation. Static electricity can damage electronic equipment. Harmonics can cause problems with electrical equipment. Power quality affects equipment performance. Energy efficiency saves money and reduces environmental impact. Renewable energy sources generate electricity from sustainable resources. Ensuring all electrical boxes are properly grounded is paramount. Any junction box, outlet box, or panel should have a reliable connection to the grounding system. This connection helps to ensure that if a fault occurs, the metal enclosure will not become energized, preventing potential electric shock hazards. The grounding conductor should be securely connected to the box using approved methods, such as grounding screws or clips. Pay close attention to boxes made of non-conductive materials, such as plastic. While the box itself does not need to be grounded, any metallic components within the box, such as receptacles or switches, must be properly grounded. Regularly inspect electrical boxes to ensure that all grounding connections are intact and free from corrosion. The proper installation and maintenance of electrical boxes is critical for maintaining a safe and reliable electrical system.